In this video, we integrate the concepts that we have developed to construct the DC to AC inverter. We decompose the inverter into subsystems. We mentioned at the beginning how in engineering design we flow the required functionality into a system design and then into subsystems that in electrical systems are implemented in circuits. One of our goals here is to better understand how a system-level design relates to functions and how those functions are implemented using circuits. Here is our system block diagram. Recall that our system, the inverter system, has an input, the energy source, which is DC, such as from a solar panel, and a load. So we have an input from the energy source, the AC output going to the load, and the conversion from DC to AC performed by our inverter. The key is that the inverter system has three subsystems: the clock source, the control subsystem, and the H-bridge. And we will discuss next how these systems interact. Let's quickly review our bridge and talk about why it's called an H-bridge. Two parallel paths, supply voltage, ground, and our load that's a bridge. And I haven't mentioned this before, but it's pretty clear what we mean by an H-bridge. Here is our H. The critical question is how to design the control that operates these switches. And remember now these switches are going to be MOSFETs. And we need some kind of control mechanism that we've seen before in block form. Our control subsystem. And we want to talk about this control subsystem and the control signals that it sends to the H-bridge. To do that, I want to introduce a term that we'll call an H-bridge dogleg. Our control system needs to operate the two doglegs of the H-bridge as follows. Now we've addressed this before, so we can go over it fairly quickly. But remember that we want in one half of the AC output the current to be flowing through this path, and in the other to flow through this path. But notice the key idea here is that we have two doglegs. Here's one dogleg, here's the other, and we want to alternately activate one and deactivate the other. Recall that in our system diagram, the control subsystem supplies the control signals to the H-bridge. These control signals are the outputs of two digital flip-flops. These outputs are called Q1 and Q2. The clock waveform here is from the clock source in the system block diagram. And in our laboratory experiment, the clock source will be a function generator. The two digital flip-flops are integrated into one chip. We label them 1 and 2. These are D flip-flops, a type of flip-flop where the D stands for data. There is one key signal that is the input to the control subsystem, the clock waveform from the clock source. It is routed to the clock inputs CK1 and CK2. Each one of these is the clock for one of the two flip-flops. Now there are two output signals from our control system, which is on this chip. The control signals Q1 and Q2. And both of these go to the H-bridge. And they are actually routed to MOSFET gates of the H-bridge. Now, finally, there are two key signals that are internal to the control system. The first is a connection from Q1 to D2, and I will draw that for you. It's a little messy, but here it goes from Q1 over to D2. And that is the Q output of flip-flop 1 here, and here's its Q output, and the D input of flip-flop 2 right here. The second is the connection from not Q2, which is this one here, and that goes from there to the D input of flip-flop 1. So our picture is getting a little messy, but we can still draw it here. There we go. Now this completes the circuit. These connections enable the control subsystem to generate the signals needed to control the H-bridge MOSFETs. Here is the schematic for the control subsystem. Here is our dual D flip-flop chip with the connections that I described earlier, plus a few more. Notice that these four connections here are all what we call pulled high to the 5-volt power supply. And here you see the clock inputs. The chip has to be grounded, and right here is VCC, which powers the chip. There is a capacitor here which is known as a bypass or decoupling capacitor to make sure that the power coming into the chip is very clean. Notice these outputs right here. They go through resistors R6 and R7. This top one comes from the Q output of flip-flop 1, and this bottom one comes from the Q output of flip-flop 2. So these are the two signals that go to the H-bridge. Here is the schematic of our H-bridge circuit. There are two important things to notice. First, the load connects between AC output 1 and AC output 2. Okay? And we model this load as a resistor. And I will draw it in here to make it clear. So our load again connects AC output 1 and AC output 2. Secondly, notice that the schematic shows 4 connections to DC input. Here, 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 and here. On your breadboard, all of these can be connected to the same 5-volt DC power supply that powers the control subsystem. Now we move on to a question. Something is different here. Why are there 3 MOSFETs for each parallel branch of the H-bridge when previously we have always considered 2. This is described a bit more in the laboratory procedure, but notice first that the Q1 signal from the first flip-flop arrives here, and the Q2 signal from the second flip-flop arrives here. The bottom line is this. When this MOSFET is turned on, I want this one off. And when this one is off, I want this one on. This MOSFET here, also known as a MOSFET driver, serves as an inverter. Notice that the Q1 signal goes directly to this MOSFET, confusingly known as Q3, whereas the signal to get to this MOSFET, Q1, has to come through this inverter. And this is because, again, when I want this one on, I want this one off, and when I want this one off, I want this one on. The same principles apply here to the other parallel branch of the H-bridge. Now, a major focus of what we are doing in ENFUSE is to show you the relevance of circuits in modern systems design. And in this case, we've talked about DC to AC inversion, particularly as applied to alternate energy systems that generate DC power, such as solar photovoltaic panels, and how to convert that power into AC so that our photovoltaic systems can be grid tied. As far as systems considerations go, though, there are a couple important things that have to happen. We have focused a lot on the fundamental design, but when you actually build these systems for use in the real world, you have to consider many other factors. And one way we talk about these is what are called the ilities. And there are many of them. I'm going to talk about 2. One is reliability, and the second is scalability. Of course, our systems need to be reliable, but that leads to the question of when we design our inverter system, how do we ensure that it's reliable in the face of problems that happen down the road? For example, what happens if one of the MOSFETs in the H-bridge burns out? Well, in our current circuit topology for the H-bridge, the result is pretty much catastrophic. If you're lucky, you might end up with a half-wave inverter and lose half your efficiency, or the whole thing might break down. So one of the questions that becomes relevant is, how do you design these systems for greater reliability in the face of component failures? The second is scalability. The design that you're going to create in the laboratory does DC to AC conversion for powers on the order of a few hundred milliamps. Of course, in the real world, we have to design systems that can handle hundreds of megaamps of power. So, for example, maybe you are working with a solar power farm and need to tie it to the grid. How do you manage that much power? So how would you scale up this design to work in a much, much larger, higher power system? This concludes our series of videos on DC to AC inversion for the energy/environment component of the ENFUSE project. To continue with this module, you'll first do the example problem. It's a simple problem on energy efficiency, and then do the laboratory experiment.